Well, good morning. My name is Michael Redmayne. I work for Caris USA, and this presentation actually blends a little bit of what I used to do working with the MB1 with Odom, and also what we do at Caris with a product a beta test of software that we're currently working on. So the scope of this presentation, first I'll be talking about the changing dynamic of survey platforms, and this is really something that I've seen working in the industry over time, and really over the last year or so, really how survey methodologies are changing. We'll then look at the operational requirement based on that changing dynamic, and then the proof of concept, which was an experiment that we did back in November of last year. With a collaboration between Teledyne Liquid Robotics and Caris. So really I put that first statement up there to be deliberately a little bit controversial, but really to say, are we seeing a shift to a more autonomous hydrographic acquisition and the more autonomous platforms that are becoming more and more prevalent these days? AUVs have been in development since the 1960s. Really originally limited in use for engineering and science, but now they're very much accepted as a viable hydrographic survey platform. NOAA are currently running through some trials to actually prove that they can accept IHO special order data off an AUV. Other countries in the world are already doing that as well. Something we've seen more so in the last 4 or 5 years is autonomous surface vessels. The real attraction here is that they can typically be built for a lower cost, a lot easier to use, and can perform many of the jobs that perhaps a manned survey vessel has traditionally done. Just to give you an idea, some of the manufacturers at ASV are here, but this gives you an idea just of some of the ones that really have come up. Some of them pretty much in the last couple of months, but some of which have been around for a lot longer than that. As ASV, I know are one that have been around for a while. And there's all sorts of weird and wonderful designs of how to essentially achieve a similar sort of thing. The one that we worked with back in November was with Liquid Robotics, which is the wave glider down on the bottom right you can see. So the operational requirement that we identified between the three companies were that autonomous platforms often lack the human control and that feedback loop. Data deliverables might be slower. You may have to actually bring your AUV back onto the platform, onto the mothership, reprocess the data before you can then go back out and do another mission. Depending on that mission, it may be, have I met coverage? Have I met data quality? Are there any holidays there? Are my sensors working the way that I want them to work? Really, you have to process the data, especially bathymetric data, before you know that. Or you could be taking a risk that you may just be going out and gathering bad data again. It could be incorrectly acquired due to the lack of that interaction, that human feedback loop. So what we identified is by actually processing or performing many of the processing tasks on board the platform, we can actually mitigate some of those issues. So a process data set may be available if there is a link, if you do have a communications link perhaps to your AUV or even your surface vessel. You may be able to actually pass over limited amounts of data, but not necessarily the full data set. So if we can actually do that processing on board the platform and then transmit it back, you can really help make decisions on that data as to how to proceed in the most time efficient manner and not waste time and money. If no bandwidth is available, an almost final data set, so this is particularly for an AUV type application, an almost final data set can be quickly reviewed. You can turn around your platform, get it back into the water to start gathering data again. So the proof of concept, and this is very much a helicopter view of the experiment that we did work back in November, really just through a lack of time to present longer. But we actually did it on the Wave Glider SV3. So for those of you that aren't familiar, this is a self-propelled autonomous surface vessel, completely autonomous. Everything is run through onboard electronics. It does have limited bandwidth for satellite communications back to shore, but it's propelled by this, this large vane structure you see down here, using wave action to actually make it move along. The concept originally was what we wanted to do is not only prove that we can do this, process on board and actually gather bathymetric data, but it was also really with a broad tenet that we were looking for large underwater objects. We weren't looking for mine-like objects, we were looking for large areas of shallow bathymetry in areas that had never been surveyed before, which was a nice easy starting point. So we chose the MB1 multi-beam because it was very small, it was very integrated, tightly coupled with a motion sensor and GPS. And the MB1 is, this is the MB1 on a skeg off the back of the platform itself. You can see it here in the water, very nice blue water. They chose to do the trials in Hawaii for some reason. And we can see the two antennas providing our position and heading here, and then SATCOMs and nav on the top. From the Caris end of things, this is the system diagram as to how we dealt with that data. So the data was acquired through the MB1 output. The way that the onboard software works is it's pointed to a particular file structure. As soon as it sees a new file appear in there, once it's generated by the system, whatever it may be, in this case directly from the MB1 as a TDY file, that's then brought into the Caris batch engine, which is the onboard process, and then it runs through the same sorts of things that you would do in Caris in processing, but it does it automatically. And that would be set up through a series of parameters which you defined before the mission had actually started. In this particular case, we were outputting, just to keep it as a simple trial, just outputting a geotiff image of the bathymetry. The mission in this case was to look for areas that were shoaler than a particular depth. So all we needed to do was look at a geotiff of what the bathy was, and we could make a determination as to whether that depth existed or not. And then it was sent over SATCOMs. So it was fairly simple. There's no reason why that geotiff couldn't be perhaps a TPU-based surface or side scan bathymetry, depending on the mission of how you're actually going to employ the platform. Give you an idea of the vessel track. The wave glider can run in different directions by adjusting the vanes on its propulsion system. So this was the vessel track as set up over a chart. This is some of the data. So in some of the areas where we experienced quite a bit of noisy data, one of the benefits with the MB1 is that because there's no real gain to interact on it, so it can actually just acquire the full data set and process afterwards. So this is what we see in Caris. So we can run a TPU filter. Area-based editing in this particular case was done after the fact, but it could be done by generating a surface and then actually filtering to that surface. This was the final product that actually came from the platform being sent over. So this is what we saw as a geotiff coming from the platform itself. So rather than getting a huge bandwidth, huge data set being sent over a very limited communications network, we could just send this image. We could say, right, this is what we're getting, and a nice, pretty picture of it in 3D. So really looking towards the future of how this may be employed is with the autonomous platforms is that this opens up the possibility of, rather than running perhaps one or two survey vessels, we could have several vessels into the water. The concept for this particular application with the liquid robotics platform is that why not send out 10 and they can all run in parallel and actually cover a very, very wide area. When you can have a low-cost platform, then that certainly does become viable, reduces your time to acquire data. And depending on how the mission is set up, you could run it with perhaps some running multi-beam, some doing SV dips, some running ADCP data, and then they could all be compiled onto a single data set, processed using the Caris on board, and then sent back. So really, to conclude, the onboard data processing certainly speeds the ping to chart time, which is a real buzzword that we have at Caris, because that's what we like to see the data work through from the ping to the chart and optimize that as best as possible. So the onboard data processing really does help that process. And it does extend resources by reducing and platform cost. Something we're actually working with NOAA right now is for them to try running and we just finished a trial with Terrason, was to run the onboard just on a standard survey launch, have it running in the background. And that meant that they didn't go out and gather all the data, come in at the end of the survey and then sit through hours and hours of processing. It was running in the background at the same time. And personally, as a hydrographer, my real attraction is that we can look at areas of high TPU, we can go back and investigate those whilst I'm still on the boat, not the next day when I've realised after processing that there's something wrong. That concludes my very brief presentation just with the time slot that we have.